All right, so no quiz due today. So instead, do the unit 4 practice problems so that you can self-assess. Are you getting the information? Are you understanding it? Also an option to get some feedback, to get help as far as the solutions are there for those. So that is up and posted. I did extend also the homework, so if you wanted to do more attempts and you haven't used up all 10 of them, you can actually do it by tonight. So those are available. Any questions about what we've covered so far? Okay, so we're going to go back to the second order solution. Oh wait, this is not you guys, sorry. There we go. Okay, we're going to go back to sine waves and phasors, wrong class. You guys are like, wait, what are we doing? Okay. So this is a continuation of last lecture, so they're the same notes, so lecture 30. And we're just going to go through the second half of them. So, okay, so I labeled them 31, but it's the same ones. Okay, so last time we talked about moving from a time domain cosine into now this new realm of plane, which is the phasor or imaginary plane. So we looked at changing a time domain signal, and I want to I'm going to back up slightly. So what we're doing is we have our time domain. We're using what we call transforms. And later on, you're going to learn that this is a Laplace transform. There's also a Fourier transform. So there are different types of transforms to move into this new space called the frequency domain. Frequency, phasor, imaginary. All of these mean the same thing. And we just call it a domain. And then we can solve a circuit using in this realm, and then we can convert back into the time domain. This one's usually an L. This one's usually an F. So here we would take an inverse Laplace or an inverse Fourier. So what this allows us to do is in the time domain, we may have a differential or an integration. And this is with time. Yes, Peter?
I was just thinking, because I think you included some pictures, but I was just kind of confused on like how to visualize like this different domain compared to like the standard that we're used to with like XY plane. It's like, I was just wondering like how to visualize it. Is it like 3D or is it still 2D?
You can still visualize it as a 2D. So here we have like our time, and then we have voltage, current, etc. In this plane, we have our imaginary axis and our real axis. So it's still an XY axis. It's just
How those correlate to each other with the transforms?
Yep, so this is one of them. So this is moving from, okay, let me draw a signal. So here we would have a cosine. And here this is going to be a vector. So let me see, a cosine omega t plus phi. or theta. And then this is going to be theta. And this is going to be your magnitude A. So that's how they're relating, is that we're changing from a cosine into this vector. Does that help visualize it better? Okay. So then we can do from a differential, we actually get to use just a variable s, which is really easy to use, and we just use it as a variable instead of the differential. This allows us in the time domain, instead of having a cosine multiplied by another cosine multiplied by a sine, which is really ugly multiplication, this just moves to addition. And it's just so much easier to add. It's complex numbers, but we can add, we can multiply, and we can divide and subtract. So much easier than a differential or an integration. So this makes it just way easier. So the idea of this is that it makes it easier to manipulate your numbers. And then once we get the right form, we can move back into the time domain. So the form that we need to do into the time domain is going to be a phasor form. So a phasor is polar. Sorry, let me do polar form. Polar form, and then we can move back into the time domain. And we move just the way we did going there, which is that we need to know that, let me go back to A, since I used it over there, A and theta, and then we move back and we get, again, that A cosine, and the omega t stays the same. And then we have, I'll do 2. So these might be new numbers. So the nice thing here is that this frequency always stays the same. All of these frequencies always just stay the same. So when we know we put a frequency in, we know we're going to get the same frequency out. The difference is it might be shifted. So we might shift it one way or the other, and we're going to change the amplitude on it. So that makes it a nice property. Then that's the way and why it works to go to this frequency phasor imaginary domain, is because that's the only thing that will be changing. So you'll learn a little bit later, there are ways when the frequencies are not the same and you have maybe 2 different frequencies coming into your circuit. There are ways to make that happen too, where you can analyze it in this frequency domain. But we're going to first look at the basics. So first thing we need to know is being able to convert from the time into this domain. So let's look at this example. Find the amplitude, frequency, and phase. And then we'll talk about it in a second. So moving into, let's write them as a capital. So what's this going to be? So amplitude is correct. Frequency. Okay, so, and you got that as, how did you convert this? Correct. So remember, omega is 2 pi f. So that becomes 3 times 10 to the 9th. And this is what units? Correct, hertz. And the 0.2 is units? Milliamps. So don't forget the milli, that makes a difference. And phase. Correct, 60 degrees. All right, so if I was to write this phasor, I would use that amplitude, so it would be 0.2 times 10 to the minus 3. And then you can do, there's two different symbols, or there's one symbol. This is the angle symbol, so you can do angle of 60, or you can write it in EJ to the 60 degrees. All right, is there anything wrong with that? Yes.
Why do you not include the negative for amps?
Okay, so the negative is not the magnitude portion, it's the phase portion. So this is actually not 60. So you have to bring in the negative. And remember that a negative cosine is a cosine, a positive cosine plus 180 degrees. So you have to bring in that negative, and that changes your phase. So this is actually written as a 0.2 milli cosine 6 pi times 10 to the 9th t plus 60 plus 180. So 80 plus 60 is 240. Or you can do 360 minus 240 minus 360. And it would be a negative angle. So either of those would be correct. So this is actually going to be 240 degrees is your angle here, not 60. Does that make sense? So that negative does have to be factored in, but it doesn't change your amplitude. It just changes it. When you put a positive in, it comes out negative. So it's flipping at 180 degrees. So it's a phase shift. Does that make sense? Okay, was there a question? Yes.
I'm just checking, but the 0.2 times 10 to the negative 3, that's just pulling it into milliamps?
Yeah. So that's because of the milli. Yep. So don't forget those millis. Just ignore this one. Okay, so I do want to talk a second about the different locations in this imaginary real plane. So if you guys remember, you saw this at one point in math, quadrants of these planes. So we say this is quadrant 1, this is quadrant 2, quadrant 3, quadrant 4. So 240 is located where? In which quadrant?
3.
Okay, correct. So this would be a vector where this is 240 degrees. This is 90. This is 180. And then this one is 270. And then the full circle is 360. So 240 degrees, and then this would have a magnitude of the vector is going to be 0.2 milli. Yes.
So are all vectors on the imaginary plane?
Oh, yeah.
Okay.
Well, the ones we're going to talk about, because we're talking about complex ones. You can have a vector that's not, but typically the ones we're going to talk about, and what you'll see in math, most of them are going to be on these planes. But you can have a vector on a different kind of plane too. So the ones we're going to look at is this imaginary frequency domain. All right, any questions? Okay, why is this important to know which quadrant it's in? So if I get, so remember that these transform from A plus BJ. And your angle is going to be B over A. So going back to the conversions. So this one, to get your angle, it's the inverse tangent of the y, which is your imaginary one over your real one. So with that, if I have a negative, say I have a -1, -j, what quadrant is that going to be in?
Or
It will be in 4 because, no? Where will it be? -1, -1. It's going to be in this quadrant 3, right? If I put this in my calculator, what is that going to give me? It's going to give me actually positive 45 degrees. Is that correct? No. So you need to be aware of where you are on this plane because you have to get the right angle. So to get this, it's going to be a 45 degrees, but it's going to be, you have to add 180 degrees to it to get you into the right quadrant. Okay? So that's why you have to be careful and understand these quadrants to make sure you are in the right one. Otherwise, you can get something like this where your negatives cancel out and give you an actual positive. Does that make sense? Yes.
So in that inverse tangent, the -j is that also -1, like you plugged it into the equation?
Yeah, this is 1 times j.
Oh, okay, I see.
Yeah. I just didn't write 1. So yeah, if it's not there, just, yeah, it would be just like j is a variable.
Okay.
So if it was y, it would be a -y. It's like 1 times y. Does that make more sense?
Yeah.
I know it's a little different thinking to think about j as a variable on an
Yeah.
axis like y. So,
Thank you.
yes, Peter?
So since it's in quadrant 3, would it be 225 degrees, essentially?
180 plus whatever 180 plus 45 is.
3 pi.
Yeah. So the actual is 180 plus 45. be, 225. Okay, all right, other questions? Okay. Okay, let's do this one. So, oh, this one's a little confusing. Let's not worry about that one. Let's just, don't worry about the lag or lead. Just convert these into phasors. So take a second and just convert those into a phasor form.
It's super cool. It's super fun.
The part three was actually so cool to filter.
I was messing with a ton of stuff. Dude. Like after I got my values, I was just like,
Yeah, no,
All right, so on this one, on the top one, you got to remember that it is a negative sign, and you want to change it into cosine first before you change into that frequency domain. So this one is cosine. 4 cosine 6 pi times 10 to the 4th t plus 30, and then you also add on the 90. So this one is going to be 4 e j to the 120, or you can write it as the big angle sign 120. So those mean the same thing. Yes?
I think I'm misinterpreting the sign chart, like how you add or subtract 90. Do you think you could go over how you make that decision over time?
Yeah, so I originally couldn't remember which way it went. So I just used Desmos and actually graphed. And then I graphed both. So I graphed negative sign, and then I graphed cosine x plus 90, and then cosine x minus 90, and it matches the exact graph of x minus 90. So if you forget, you can always go and graph them and then re-see what they are. If you're trying to memorize and remember them, it's opposites. So if you have a negative, this one will be plus. If you have a plus, this one will be negative. So that's kind of how you can memorize them. But as I said, if you don't use them all the time, you forget. Just go graph them, and then you can say I know it shifts one way or the other.
So if we have a negative amplitude, are we gonna wanna transform however so we don't have that negative? in our
Correct, yep.
equation?
So you gotta take that into account because you have to understand, so that's a concept understanding of understanding that negative means a phase shift
Yeah,
and not a magnitude change.
so we need to take that into our phase shift.
Yep, so you have to account for it in that phase shift. So always take that negative into the cosine. All right, other questions? Yes.
Now, does the frequency not really show up at all in our phasor?
Correct.
ones?
Yep, it comes back when you go back into the time domain. That frequency will stay the same, so your cosine that you after you've, so what this is an input signal, and then we're going to next learn how to like manipulate the components so we can use them in that domain, and then we can do Ohm's law, we can do voltage dividers, current dividers, node voltage, and now we just do it with complex numbers in there. And so we can then find a solution for the circuit based on this particular input, and then we change it back after we get that equation that's in S form or J omega form, depending on which one. We'll get into that in a minute. But whichever form it is, we can then go back to the time domain. And with a particular input, we use the same input frequency. And then we just change it back into that same frequency, and it will have a magnitude and a phase change difference. Does that make sense? Okay. All right, so any other questions on this one? Okay, the next one is going to be, is a little easier because you just change it over. So this is just going to be 2e to the negative j30 degrees, or 2 angle negative 30. Yes?
Could you, like, if you didn't want a negative 30, could you in theory go plus 330?
Mm-hmm. Be 360 minus 30, so yeah. Yep, that would be the same thing.
What would you recommend doing?
Whichever one, to me, 30 minus 30 looks easier. Like, I know that one, but some of them, it's just more preference. MATLAB, I think, always goes in a positive rotation. So some of the tools you use may have its own designation, like it will always give it to you in one way. So just note that, but it ends up being personal preference, just so you know for sure, like where are you in that plane and is that the right angle from your result. So you do kind of want to check that. So that negative 30 or 330 is going to put you in which quadrant? Correct. This will be the fourth quadrant. So the one you have to be wary of is that third quadrant where you get a negative and a negative, and so it looks like it's actually in the first quadrant because it will give you a positive angle, but it's not. You got to know it's going to be a different answer if it is. So, all right. So we already talked about like where we have Cartesian coordinates or polar coordinates and rectangular coordinates. So for the polar, we are really wanting that magnitude, and then in rectangular form, so this is also, you'll see rectangular or Cartesian. They mean the same thing. So you can have A and B, so this would be A plus BJ, or RE to the J theta. All right, so let's see. So this is kind of, the general form is in the time domain, and then in the phasor domain, that would be your your form. Yeah, we'll not get into that yet. Okay, so let's transform these into let's just do this one. So do I3 and change that into phasor form. So we already did examples like these others. I'll just write them if you want practice. But go ahead and work on that I3. Go. Sorry. All right, so these would be the phasors for all of these. What do we do now that we have two polar forms that want to be added? You're gonna love my answer because I make errors all the time in conversions. So. Okay, so when you use Wolfram, you want to make sure that you are using I and not the J. So remember, J we use because we don't want to confuse it with the current I, but every tool that you're going to use uses I as that imaginary number. So you make sure you change that back. So simplifying this, just 8 times e to the minus I times 45 degrees, and if you don't put a degrees, it will default to what do you call it? Radians per second. No, it's not liking this. If I degree? Okay, so maybe not. Okay, it's not liking this. So I'm gonna figure out why it's not liking it. Oh, minus. Nope, still not liking it. Okay. So every tool will also have a way of converting. Okay. There's a list that I came across. Not it either. So from polar and to polar coordinates is the one you can search for them. So from polar, we can convert these, get them into rectangular form, and then you can add them. Oh my, this is not working at all. From polar coordinates. And then you want to make sure you're in the right format of what it wants. Okay, not working today. From polar coordinates. Okay. Okay, I don't know. I will do this next time. But you convert it to rectangular, then you can add them. Just add the real portions, add the imaginary, and then convert it back into the polar to then transform it back into the time. Okay. All right. Oh, we do have time. Okay, we are going to go on. So simplifying the expressions, I would use a calculator to do those and not just do them by hand. It's good to practice them a few times, get that exercise in, but then I always use a calculator to convert them. Okay, the other components we want to change. All right, so final project is coming up, so do make sure to think about it. If you have any questions, you can chat with me or you can chat with any of the TAs. So the idea is to use some type of sensor, create a circuit that's processing the signal from that sensor. A lot of times that's going to be an op-amp. I would like you to try to use an op-amp, at least one in your circuit, but understand if you don't, most of them, all of them have to have an op-amp in there to be able to do at least something, whether it's buffering your signal so that it keeps it the same voltage. So if you put on your output, you're not, like if it's a speaker, you're not diminishing all your sound out of it. So it can be something simple like that where you just use a buffer to help create that buffer in between the output stage. So the output should be something that is visible or audible. So sound, any of these ideas in here. So you can do anything that your creative mind can come up with that sounds fun and interesting to you. So do make sure you're working on that. You guys already probably have started into this, so making sure you've submitted your design idea and that you're working on it to get your specifications. I encourage all of you to test your sensors. So if you get a sensor, do make sure to create a new test environment. So if it's a photoresistor, for example, test it at different light illuminations so that you're getting different values so you can figure out exactly where you want your threshold to be. So it's called characterizing the sensors. So that's good exercise to do as an engineer, is to be able to understand, as I change my light intensity, what change am I seeing in that photoresistor. So creating a plot is great of something like that, where you have a change in increments and then you test over all these changes and then you put exact plots for every single one of them on a graph. And then you can see, is it a linear? If I was to graph that, is it acting linearly or is it acting as a nonlinear where it's not quite linear? So a lot of times you're gonna get data points that kind of look like this, that you're gonna wanna also learn how to kind of fit that data by an expected kind of line. So these are some things to work on. The thing that we'll need to know next is moving from, we've done the signals now, so the elements themselves, moving into that frequency time domain. So the Laplace transform you have not learned yet in math, but in math there is this thing called the Laplace transform that does help you convert from the time domain into the frequency domain. And what it has, which is really nice, is that when you have a differential, you're able to get an S variable in that frequency time domain. So your resistor doesn't have any time dependence or any differentials, so it stays the same. For your capacitor, remember your capacitor was C, dV C dt is equal to IC. So now this becomes an I and a capacitor, and this becomes S times VC. And remember, for resistance, it looks like I times Z, and Z is just meaning that we're now in this complex, so we call it an impedance instead of resistance. So what would your resistance here look like? It's going to be 1 over CS. And then for the inductor, you had VL was I, or L di L dt. So this becomes VL L SIL. And your impedance here is SL. So now we treat them just like resistors, and we can analyze the whole circuit using that. So that's what we're going to get into next week. All right, any questions? I think I saw hands. No? All right, see you guys on Monday.
I have one question for the projects, at least. So I've been looking more into